Next talk today is a science highlight on PFISR science. The first 3 years of PFISR given by Josh Semeta.
Well, I'm here to say something about the first 3 years of operation of the PFISR facility, the poker flat incoherent scatter radar that Rich talked about. I'm sure that Bill Gordon would be extremely proud, and I don't know, maybe I shouldn't be, but I'm kind of shocked and in awe of how vital this field remains. Every time somebody I hear from somewhere tries to paint this as Cold War technology and, you know, sort of been there, done that, something brand new comes up. And you can mark my prediction. I think there's going to be a real large-scale resurgence of radio science in the coming years for, for a lot of reasons. And in the ionospheric area, certainly the AMISR project. So we decided that after 3 years of operation, we ought to all convene somewhere in by we, I mean the people who were willing to fly to Fairbanks in February, up and see, you know, where we stand with this facility and the kind of things that have done. So we had roughly, we had 35 people who made it up to Fairbanks, and this is the, well, you can see there's a generational difference between Rich and I. Rich had to press a button to do this, but this is the. As Rich mentioned, these are, you know, we have ISRs all over the world, and they remain, the publication rates, citation rates remain really high. And so I'm going to talk mostly about of course, the poker flat incoherent scatter radar. This marks the return of incoherent scatter to the auroral zone under U.S. auspices. And and it's also marked the return of the U.S. to a leadership in the ISR technology area. So I would like to think that we sort of leapfrogged over ISCAT, and they're in turn trying to do the same to us now. But this is a partial. This is about half of the meeting attendees up at Fairbanks, standing in front of the facility. Of course, I'm not in the picture because, you know, the radar would appear a lot smaller if I were. And so they actually took a separate picture of me in front of the facility. Craig asked me to change out one of the antenna element units, so I was working on that. This picture. All right, so as a 20-minute talk here, I gave a tutorial on how ISR works at the GEM meeting just recently, and I'm going to give you a 5-minute version of that 45-minute tutorial. I know there's a lot of students in the room, and we all pretend that everybody somehow knows how this diagnostic works, but let me try to make it as simple as possible. It's a Doppler radar, just like a Doppler weather radar. Okay? We send out a signal at frequency F, and it comes back at a slightly different frequency, and we can gate that in range. So we have a measure of velocity versus range and time. The two key concepts in radar are that distance equals time, right? So range is related to time as we gate the returns, and velocity is synonymous with frequency. So changes in frequency give us the indication of the velocity field. And so a Doppler, this is one of the next rad radar results. You know, what would a standard Doppler radar see if it looked into a tornado? This is going away from us, yellow, and coming towards us is green. And so you can see what we get, of course, is a line of sight projection of the velocity field as a function of range as we scan through the thing. And we see this gap in the middle, of course, where the winds are blowing completely orthogonal to us, so that velocity becomes invisible. So this is just single velocity as a function of range. Now, what happens if the target's sort of moving in the scene, or we leave the gate open on the receiver and we integrate for a while? If we were looking at a bird, for instance, we'd see a spectrum of velocities, and we'd have kind of an average of all those velocity returns coming back. And so then we get into the concept of a Doppler spectrum. And so this is measurements from, again, a weather radar, and there's a bird in the field of view, and there's also a wind field at the same time. So then all you have to ask yourself is, what is the Doppler spectrum of the ionosphere? We have a target, right? You know, everybody knows that radiation reflects off electrons, so there should be some Doppler spectrum associated with the random motions of the electrons. And can we predict that theoretically? Well, you know, it turns out we can. And I decided this might be a nifty way to show this. This is a density fluctuations as a function of time and space that come from a plasma simulation, a particle and cell simulation. This is a code that Mears Oppenheim developed. And you know, your eye doesn't pick out any kind of coherency whatsoever. Okay? But there are theory tells us that in a thermal equilibrium plasma, there are two longitudinal modes that should pop out, the Langmuir mode and the ionoacoustic mode. And so if you took a Fourier transform of this in space and time, you can come up with what we like to call a dispersion surface. And you'll see that what looks very incoherent here actually has these coherencies involved in the power. So there's power associated with the ionoacoustic line, or the ion line. And then there's other coherencies here at frequencies offset by the plasma frequency. And those are the Langmuir modes, or what we commonly call the plasma line. So this is wavelength, essentially, versus frequency. So as I just mentioned, what does a radar do? Well, a radar has a very particular K, a very particular frequency. So if we blow up the ionoacoustic line, it looks like this little spray here. And each radar that we build has a certain specific frequency, so it has a certain specific wavelength. And so we take cuts through this. And if we flip that up on end, we get something that looks like this. So that's ISR. It's a Doppler spectrum at UHF, and it's somewhat dependent on frequency. Why don't we see sharp lines at the ionoacoustic speeds? Because of Landau damping. So we have ionoacoustic modes that are Landau damped. And so you can imagine that there is a forward model for the Landau damping and for the ionoacoustic modes. And we can write, in fact, exact equations, this is from Evans et al., for what that spectrum should look like. And all we have to do, quote unquote, is to come up with some software to pull out these parameters to estimate them in some optimal sense based on the measurements. And roughly speaking, you can look at things this way. Craig kind of put together pictures like this in the past. That the width, or basically the separation of the ionoacoustic lines, is related to the ratio of the ion temperature to the ion mass. The amount of Landau damping, or the dip in the spectrum, is related to the electron temperature. Roughly speaking, the area is related to the electron density. And then we look for a Doppler frequency shift, a bulk Doppler frequency shift. And that tells us whether the bulk plasma is moving towards us or away from us. Now, for those of you who actually do the radio science involved, of course, it's much, much more complicated in terms of how we estimate that spectrum. But let me just say that you actually have to average an awful lot of returns, because you're estimating the mean behavior of a random process. So if you just took one sample of the ionosphere, you'd get nothing that looks very much like that double hump spectrum at all. As you take more samples, your confidence goes up as 1 over square root of the number of samples. And so you have to integrate for a while to do this. All right. So I'm going to get to PFISR in just a second, just to give those of you who don't think about the auroral zone very much a little context. This is a beautifully well-controlled event that we've studied up at Sonderstrom, where we have a poleward boundary intensification, a particular kind of aurora that passes into the field of view of the Sonderstrom radar. And so we can stare straight up and see what's happening to those parameters that we fit with ISR. And you can see that at high latitudes, it's just incredibly variable. Incredibly variable. We see the auroral ionization start to appear here at low altitudes. Just preceding that, we see hot ion temperatures indicative of strong electric fields outside of the aurora. We see hot electron temperatures inside, at least for part of the aurora, and that tells us something about the acceleration mechanism. And then we see ions flowing out of the ionosphere. Lots of physics comes out of pointing an ISR into something in the auroral zone. All right, so this is the dish versus phased array. This is a beautiful time lapse that Craig Heinzelman produced of the Sonderstrom radar cycling through what they call the composite scan mode. Each one of those cycles in that picture is about 20 minutes long. And that's how we get our spatial information. On the right is a movie of PFISR scanning. So one thing I want to mention, though, of course, is that the phased array approach it's a new modality for ionospheric research, but it's in no way a panacea. There are actually trade-offs, of course. The field of view of Sonderstrom is horizon to horizon, essentially. The field of view of PFISR is roughly plus or minus 15 degrees from boresight due to these grating lobes that appear. But then the advantages kick in: integration over all positions simultaneously. We define beams, and we can do that coherent integration over all positions. The power is distributed, no moving parts. The power distributed is the first interesting highlight that I'll mention. Suppose you wanted to just sample over the course of a year, 2 years, 10 years, just one sample in the zenith and at a 15-minute cadence or something like that. It'd be impossible to do with something like the Sonderstrom radar because you have to start up a 4-megawatt klystron to do that every time. PFISR, it's apparently simple, but it looks simple at least to those of us who just used the facility and didn't actually build it. But over the course of the International Polar Year, this is work by Soik et al. They took measurements of TI and looked for these so-called co-rotating interaction region events, which are these sort of localized streams of enhanced solar wind streams coming out of the sun, and looked for their effect on the ionosphere. And so this is such a repeatable phenomenon that you can do something called an epoch analysis, where you put the 0 point at the same point in the event every time and look at the mean behavior. And you can see that the ionosphere has a clear response. This is something called a cumulative distribution function. But you can just think of it as the average behavior of the ion temperature as relates to a particular point in this type of event. And so here PFISR is showing us a clear view of the change in the ionosphere related to these things. Another advantage, as I mentioned, is this electronic steering. We can actually take a large number of beams and spray them over the sky and sample them all together and try to build up a picture of what's happening in the ionosphere. It's a particularly interesting thing to do in the auroral zone, where we have things like on the right here. This movie doesn't look like it comes out very well, but this is a substorm at about 100 times real time. This is all sky images, and we planted the beams in the field of view. And so if you were just pointing a single beam into that, it would be difficult to get the contextual information that you can get out of PFISR. So this is a result that I know many of you have seen probably numerous times, but I'll show it anyway. The lower panel is what you might observe if you didn't integrate very long and just looked into the zenith. And we see what we have here is a diffuse precipitation leading up to the substorm. This is electron density, where the ionization increases. And then afterwards, this is the substorm recovery phase. And so if you take a pole and stick it through the sort of middle of my three-dimensional view here and run it along here, you can kind of get a good picture of the type of information that's sort of missing from this display. So these are cuts at 100, 110, 120 kilometers of the ionization produced by this substorm, and then a back pane. So you can kind of get, this is just our way of displaying the three-dimensional information. And so this movie was produced by my graduate student, Thomas Butler. And so there's a lot to be said. There's several publications sort of in process on the sort of things we're learning from this kind of perspective. Now, this idea of imaging using multiple beams has not just been limited to auroral work. This is some work by Taylor et al., where they were looking at PMSEs, polar mesospheric summer echoes, and noctilucent clouds simultaneously with PFISR, and multiple beam positions with PFISR, and also with a LiDAR. And so this is a nice color photograph of this phenomenon. And so you can do the same thing. You can construct, these are cuts at different altitudes. You can construct the volumetric distribution of the returns from these much lower altitude phenomena as well, using these same techniques. And now the next thing I want to talk about is another thing that you can do with PFISR that's kind of interesting. You get these line-of-sight velocities, as I mentioned, Doppler spectra at each position, and you can construct for yourself an inverse problem to figure out what are the convective flows as a function of position. This is one result that we published that shows an interesting combination of the different diagnostic information that's available. What we see here is an auroral brightening in an all-sky camera image that's been cropped a little bit. And these flow arrows, this is the ionospheric convective flows, and you can see that they're abated right at where the auroral activation is. And we expect that because the flows are related to electric field, and the electric fields become attenuated where the conductance increases. So this is sort of expected physics. Also placed on here are contours of ion temperature at 300 kilometers, showing also what's expected, which is a reduction in the ion frictional heating associated with that reduced electric field. So you can start to piece together a pretty interesting picture imagine being able to do this at 30-second cadence or something like that. I mean, these are the sorts of things we're trying to figure out. You know, what is the limit of the temporal resolution that we can do with that? Now, there's a lot of talk at the GEM meeting I was at about this sort of physics that Larry Lyons and Shasha Zhao and Toshi Nishimura and other people have been thinking about. And I won't talk too much about the physics here, but there's this interesting little, in the convection pattern, right near substorm times, you see this interesting little anomaly here called the Harang reversal region that becomes enhanced. And this is produced by a differential curvature drift out in the magnetosphere, and it's producing a divergence of the current system out there, which has to close in the ionosphere. So it produces this thing that we, you know, unbeknownst to us in the CEDAR community, we point radars and optical devices into this feature all the time, but we may not think about them quite in terms of the magnetospheric context. This is one reason why we want to have something like a joint GEM CEDAR meeting next year. Okay, so you know, Larry Lyons and his colleagues have been looking at this feature. This is a composite movie from the Themis ground-based observatory produced by Eric Donovan and his student, I guess, Emma Spanswick. This is an amazing resource. We have to figure out how to keep it funded even after the Themis mission goes away. So we get these global scale perspectives of the auroral patterns, and this box here is the PFISR observations. And what you saw in there was a sort of a loop of aurora passing through. And it turns out that loop is in fact related to this Harang reversal, and we can prove that with PFISR. So these are PFISR observations of that quiet auroral arc that was sitting in there. And these are the arrows that have been reconstructed from this inversion technique that we produced. And as this loop structure passes through, I know you can briefly see that the flows actually follow the loop pattern around. This is a relatively brief talk, so I won't, we've kind of outlined it in further detail here. And you can check out, there's a radio science article by Butler et al. That's coming out that's soon that'll show these things. Now again, as I said before, you know, of course my personal interests have a lot to do with the auroral phenomenon, but these same techniques have been used in other domains. This is work by Nichols et al. On winds and gravity waves in the D region. Now, I think this was, if I'm not mistaken, rather unexpected that PFISR is seeing returns down to 60 kilometers. And so there's some ionizing source, at least on occasion, that's giving us a signal that we can play with down at 60 kilometers. Now, at these altitudes, your ionosphere is very tightly coupled. What remains of it is very tightly coupled to the neutral atmosphere. So the radar is, in fact, looking at neutral atmosphere dynamics. And if we look at different positions, then we can see different wiggles. This is frequency offset. So this is your Doppler spectrum. You're almost using it just like a Doppler radar, a weather radar. And so what Nichols has done is looked at multiple beam position and is able to infer information about the gravity wave field, and has done a lot of analysis of the spectral content, and you know, this one highlight here that the increase in the wind speed correlates to a decrease in wave amplitude, and all kinds of interesting stuff has come out of this work. Last topic I think is, well, what's that? 3? Good, perfect. Okay, so another topic I really want to mention, I think this is going to end up being a big deal, is low altitude ionospheric turbulence. This is a movie that I recorded at Poker Flat in 2007 with a narrow field camera. So this is an 11-kilometer field of view, 30 frames a second. So this is real time. I won't talk about that. But these are the PFISR beams that it turned out that Anja Strome was operating an experiment at the same time, looking directly into this stuff. And not only that, she was looking into it with a raw voltage mode. So we could play around directly with the raw voltages and see what we get. And this is a phenomenon that's popularly known these days as NEALS, or naturally enhanced ion acoustic lines. This is just raw power, and down here, this grass down here at the bottom is the auroral ionization. But above here in this region, we see this enhanced power that is absolutely not a thermal plasma, thermal ISR phenomenon. The blue curve is the optical intensity, so this just tells you where things are correlated with that. People have been thinking about this for a while. Michelle and Samara and have published a few papers using PFISR data to study this thing. But what we did most recently, is to produce region-specific autocorrelation functions. So we take a region where the plasma looks self-similar, looks thermal, and we produce a spectrum as a function of altitude. So this is what the ISR spectrum looks like as a function of altitude. Then we take these other regions, 2 and 3, and do the same thing, and we get some very unusual looking spectra out of this thing. This is our kind of enhanced, our classic enhanced ion line sort of thing. Earlier we see some other kind of turbulence that we haven't yet explained entirely. Last thing I want to show in my 1 remaining minute is just some initial results from RISER, which is the Resolute Incoherence scatter radar. And incidentally, the Canadians are going to have just apparently purchased another face to face the other direction. An initial look at the polar cap. This is some stuff that Nichols gave me. I guess it's unpublished. I've never heard of anything by Nichols that's unpublished before. But so apparently things are very, things are very variable. This is diurnal variations that you see, this little dip down here, and these highly structured polar cap patches above. And one of the initial results that's intriguing is the behavior with solar zenith angle of the ion temperature in blue and the electron temperature in black. Normally we expect this situation where they're nearly equal or the electron temperature exceeds a little bit. But it turns out at high solar zenith angles there's something going on with the spectrum. Standard ISR analysis produces ion temperatures that far exceed the electron temperatures. And I believe the SRI Brain Trust is working on that problem. So what is yet to be done? Last slide here is just, we've been working at 3 years and we're learning a lot as we go. Radar mode development is we need to think about, and this is a collaboration between people who think about radio science exclusively, and so we still have work to do there. Assimilation with ancillary diagnostics. They just put a couple canonical representative pictures down here. This is some work by I believe the 30 megahertz radar of Dave Heisel, and he's done some work putting this in the context of ISR, and I know he has a lot more that he wants to do with that. This is a picture which I won't talk about at all. You can all go find Christina Lynch and ask her to explain it. This is rocket measurements of poleward boundary intensifications, where we also have good PFISR measurements of what's going on. So these conjugate studies as well. So that's it. Thank you.